Good morning, everyone. In today's video, I'll be talking about the completely fair scheduler. So the contents is the overview, few implementation details, the RB tree, some features of CFS, scheduling policies, scheduling classes, and the last one is group scheduler extensions to CFS. Completely Fair Scheduler. CFS stands for Completely Fair Scheduler and is the new desktop process scheduler implemented by Ingo Mornar and merged in Linux 2.6.23. It is a replacement for the previous vanilla scheduler sched other interactivity code. So 80% of CFS design can be summed up in a single sentence. CFS basically models an ideal, precise multitasking CPU on real hardware. Ideal multitasking CPU is a non-existent CPU that has 100% physical power and which can run each task at precise, equal speed. In parallel, each at 1 hour running speed. For example, if there are 2 tasks running, then it's run each at 50% physical power. So example is actually in parallel. On real hardware, we can run only a single task at once, so we have to introduce the concept of virtual runtime. The virtual runtime of a task specifies when its next time slice would start execution on the ideal multitasking CPU described above. In practice, the virtual runtime of a task is its actual runtime normalized to the total number of running tasks. Few implementation details. In CFS, the virtual runtime is expressed and tracked via the per task PSE.vRuntime nanosecond unit value. This way, it's possible to accurately timestamp and measure the expected CPU time a task should have gotten. Small detail, on ideal hardware at any time, all tasks would have the same PSE.vRuntime value. Tasks would execute simultaneously and no task would ever get out of balance from the ideal share of CPU time. CFS task picking logic is based on this PSE.vRuntime value and it is thus very simple. It always tries to run tasks with the smallest PSE.vRuntime value, the task which executed least so far. CFS always tries to split up CPU time between runnable tasks as close to the ideal multitasking hardware as possible. Most of the rest of CFS design just falls out of this really simple concept, with a few add-on embellishments like nice levels, multiprocessing and various algorithm variants to recognize sleepers. The RB tree. FS design is quite radical. It does not use the old data structures for the run queues, but it uses a time-ordered RB tree to build a timeline of future task execution and thus has no array switch artifacts by which both the previous vanilla scheduler and RSDL or SDR affected. CFS also maintains the RQ, CFS that mean vRuntime value, which is a monotonic increasing value tracking the smallest vRuntime among all tasks in the run queue. The total amount of work done by the system is tracked using mean vRuntime. That value is used to replace newly activated entities on the left side of the tree as much as possible. Some features of CFS. CFS uses nanosecond granularity accounting and does not rely on any GVs or other HZ detail. Thus, the CFS scheduler has no notion of time slices in the way the previous scheduler had, and has no heuristic whatsoever. There is only one central tunable. You have to switch on config sched debug, which can be used to tune the scheduler from desktop, low latencies, to server, good batching, workloads. It defaults to a setting suitable for desktop workloads. Sched batch is handled by the CFS scheduler module 2. Due to its design, the CFS scheduler is not prone to any of the attacks that exist today against the heuristic of the stack scheduler. 50p.c, tad.c, chew.c, ringtest.c, massive int r.c all work fine and do not impact interactivity and produce the expected behavior. The CFS scheduler has a much stronger handling of nice levels and is sched batch than the previous vanilla scheduler. Both types of workloads are isolated much more aggressively. SMP load balancing has seen reworked or sanitized. The run queue walking assumptions are gone from the load balancing code now, and iterators of the scheduling modules are used. The balancing code got quite a bit simpler as a result. Scheduling policies. CFS implements three scheduling policies. Sched normal, traditionally called sched other, the scheduling policy that is used for regular tasks. Sched batch does not print nearly as often as regular tasks would, thereby allowing tasks to run longer and make better use of cache, but at the cost of interactivity. This is well suited for batch jobs. Sched idle. This is even weaker than NICE 19, but is not a true idle timer scheduler in order to avoid to get into priority inversion problems which would deadlock the machine. Scheduling process. This is the partial list of the hooks. Enqueue task. Called when a task enters a runnable state. It puts the scheduling entity task into the red block tree and increments the NR running variable. The queue task. When a task is no longer runnable, this function is called to keep the corresponding scheduling entity out of the red block tree. It decrements the NR running variable. Yield task. This function is basically just a queue followed by an enqueue unless the compat yield SYSCTL is turned on. In that case, it places the scheduling entity at the rightmost end of the red block tree. Check prim cur. This function checks if a task that entered the runnable state should print the currently running task. Pick next task. This function chooses the most appropriate task eligible to run next. Set cur task. This function is called when a task changes its scheduling class or changes its task group. Task tick. This function is mostly called from time tick functions. It might lead to process switch. Describes the running preemption. And the last one is a group scheduler extension to CFS. Normally, this scheduler operates on individual tasks and is strived to provide fair CPU time to each task. Sometimes, it may be desirable to group tasks and provide fair CPU time to each such task group. For example, it may be desirable to first provide fair CPU time to each user on the system and then to each task belonging to a user. Config cgroup sched. It strives to achieve exactly that. It lets tasks to be grouped and divides CPU time fairly among such groups. Config RT group sched. Permits to group real time. Sched FIFO and sched RR tasks. Config fair group sched. Permits to group CFS, sched normal, and sched batch tasks. So that's all. Thank you.